All right. So here are the notations for kind of like algebra functions. This is the easiest way to describe this. So if you see f plus g inside and an x, all that means is add the function f, add the function g. And we've mentioned this a little bit already. The difference, same thing, just subtract them. If you see a times, we'll multiply them together. Okay. I don't think they're going to ask, but just in case, if the domain of f is equal to a and domain of g is b, then when you add them together, the domain becomes the intersection of those two domains. The difference would be the intersection. Multiplication is the same thing. The only one that changes a little bit is number 4. Because you're dividing, you have a potential for division by 0. So it's still the intersection, but you also have to consider this. So A intersect B such that G is not 0. Okay. So just some quick notes there. And if you saw the videos and read the book, then you already know all that stuff. But just in case, it's a quick overview on this. All right. So first example. It's pretty easy actually. Evaluate given f of x equal to x plus 3 and g of x equal to x squared minus 2. So they want us to evaluate this. So it wants us to evaluate f plus g of -2. So this is example 1, problem 1. So all this means is plug it into both, right? No big deal. If it was times, well, you'd have a times here. If you have a minus, you'd have a minus. So nothing crazy. So f of -2 would simply be -2 plus 3. You just plug it into this function, plus the g function at -2 squared minus 2. That would be 1 plus 4 minus 2, which obviously is 1 plus 2. Any questions on the notation? That's all this really is learning what the notation means and then plugging in numbers. It's nothing new really. It's just knowing what these notations mean. That's it. Okay. Example 2. You guys cool so far? Actually, let's move on to something a little more difficult. I feel like that's too simple. So next example will be problem 5 from the homework. All right, given, I forgot to write. Given that f of x is equal to x plus 3. And g is equal to, I don't have space. Let me see if I can fit it in there. All right. So given the following, our A says, find f plus g of x. Okay, so that means we said add f and g. So that will be x plus 3 plus x minus 3, which gives us 2x. Nothing crazy. Part B, we do the difference. You guys okay so far?
Yes.
Yes.
Okay. So subtract, just be careful with the signs and you'll be okay. So I'm not going to do too many of these because we have talked about this already. So minus, that'll be x plus 3 minus x minus minus will be a plus 3. Oops. That'll be a 6. Okay. C. I'm going to change the question a little bit. Find the domain of f and g. What's the domain of f? So here's f right there. You agree it's a line, right?
Yes.
So there is no issues plugging in numbers. You can plug in whatever you like without issue. So if you graph it, you'll see it for sure, but it should be obvious that it's all real numbers. And g is the same thing. It's just a different line. Okay.
Is it okay if we put R for all real numbers?
Yeah, that's fine.
Got
The homework, I think we might write it this way for certain problems.
Yeah, but when like tests come and all that kind of stuff.
Yeah, that's fine. Any questions on A, B, or C?
I cannot see the C very well. That's better.
Okay. I'll wait a bit. Okay. So everyone agree that this is the domain for f and g. Does everyone see why that is? Because I need to understand this part for part D. So let me know if something doesn't make sense. Find the domain of f over g of x. So we know that f over g of x is equal to f of x divided by g of x, which would be x plus 3 over x minus 3, right? So technically, we need to find the function first. And then just look at it and see, okay, well, in the notes, we said, we turn back to the beginning. We said the domain for a quotient type is the same thing, you just combine them together, but remove these. So for the domain for this one, you would just combine this one and that one, which is the same thing, right? If you combine the same all real numbers, it's still all real numbers. Does that make sense? Only this one's a little different though. So what causes division? What causes G to be 0? The bottom part.
3.
Yeah, we can't have 3. So technically we could write it this way in plain English, right? Domain is all real numbers, right? Except, oops, x cannot be 3. Right? You could technically just say it straight up in the sentence or whatever, but as a interval, you would say, well, everything except 3 means that you have a hole in the middle and everything else is cool. So you'd say, well, everything after 3 is good, but don't include 3, so no brackets. Everything before 3 is fine. So you would write this as negative infinity to 3 union 3 to infinity. This is the domain as an interval. It's using this drawing here. That make more sense, or? Okay. So let me show you the homework. Okay, can you see the homework?
Yes, sir.
Okay, sorry, it looked strange on my end. Okay, so we did this one. So you just find them real quick, and then they ask you to find the domain of the last one. So they're gonna have you write it as an interval. Okay. The first few is just literally just doing like find f plus g, then plug in the number. Or you could plug it in all at once if you want, but I'd say just do it separately like we did. Same thing for the difference and the times. Let's see, is there anything else worth talking about here? Okay. Graphic types. Well, I guess they start talking about a composition, so we got to talk about this. Just a moment. Okay, so remember what we said here, right? We said this means f minus g. So part A is basically saying find f of -1 and subtract g of -1. So f of -1 means you're plugging in -1 and getting a y value. Right, so this part is right here. F of negative, here's f right here, f of -1. Oh, I'm sorry, it's a positive. Shoot. Let me erase that. So f of 1. So go to the x value on your f graph right here. So f of 1 means I get an output here, right? So this is actually 2 minus g of 1. Well, here's 1. At 1, the g function is 3. So this is the output. So you're subtracting the difference. And you're getting -1. That's how they got this guy. Okay. Part B is just times. So you'd have f at 3. Times g of 3. So go to 3. It's right here. F is 2. So this is that is f of 3. So 2 times g of 3. That would be here. The other one was over here. 1. So 2 times 1 is how they got 2 over here. That makes sense? Any questions on this graphical example? We did the analytical side. This is the visual side.
I do have one question. 10, the symbol that is that the multiplication symbol?
No, we have not talked about that yet.
Oh, okay.
Unless you read about it, we haven't talked about it. We got to write some notes first. We'll do that in a second. Any other questions for number 9 at least? Okay. All right. So we need to talk about composition. Well, you've seen the video. There's some theory background. So if you see the symbol, so number 1, F composed with G, that's what that means. Looks like fog. F of G of X is what it means. It means you're inputting the G function inside the F function. You're composing them together. And if you have it written the other way around, golf, G of F of X, you're inputting the F function inside the G. So finding that is not too bad. The hard part is finding the domain. Okay, the domain of fog will depend on the G function. So whatever's going inside is the one that's going to dictate what's going to happen to f of G. So you look at the inside and see, okay, what is the issues? What are the restrictions on G? Because those restrictions will carry on to the composition. So f of G will be dictated by G, but then if you result in a new restriction once you do the algebra, then you'll have to take those into account. So you take into account the restrictions of G and the restrictions of fog. That's how you find the domain of number one of this. 2 is the other way around. You look at the one going inside, the f, find out what those restrictions are, then find out if any new restrictions appeared once you plugged it in. And then you write all those restrictions together and make your domain. It'll make more sense once I show you, but that's the idea. So you always look at the ones going in and then look at the results and then put that together. Just to put it simply. Example. Okay. Let's find one that's a little harder. Let's do number. Use number 12 first. You can see how it works. So find fog, Goff, and fog, I guess. Given f of x equal to x squared and g of x equal to x minus 1. Okay. So part A, fog. So that means f of g of x, which means f of, so here's the f, plug in g. So I'm going to go ahead and write it out so you can see it. X minus 1 is going inside the f, which means, what does f do, right? F squares stuff. So square that input. That gives us this result. So this is fog. Any questions on part A? Okay. G of f. That means you're plugging in x squared, which is the f, into this g function. So this becomes minus 1, right? I put these parentheses so you can see that it's going in here. These parentheses did nothing. It was for emphasis. So there we go. Okay, so g of g means plug in the g inside the g. Which is kind of weird, right? G of x minus 1, that's what it told me to do. Here's the g, and I plug it into the g. What does g do? Well, it takes your input and subtracts 1, right? So this is my input, subtract 1. So we get x minus 1, which is x minus 2. That's G of G. Any questions on A, B, or C? That's how they got these results. They didn't multiply part A, but they could. Anyway, 13 is the same deal. 14 is similar. This is the part that's a little harder. Let's do 15 in just a moment. 10 is the visual part. So let's go ahead and do part A together. So remember what fog means. F of 2 means F of G of 2. So G of 2 would be right here, right? So plug it in 2 gives you a 2. So this is the result inside would be a 2. Then you go, okay, well, F of 2 is right here. F of 2 is 0. That's how they got this. Any questions on number 10? I'll let you do part B. The same thing, just the other direction. Okay. What's up?
Isn't that also 0?
Other direction will not be 0. Because it would be G of F of 2, right? So F of 2 would be 0. So that would be G of 0, which is a 4. 0 is right there.
Ah, okay. I guess I skipped that part. Didn't think we had to go back to the other graph.
Yeah. Just remember like what this means, right? To just break it down little by little so you don't get it all backwards. Okay, let's do the domain part because that's the hard part. So given f of x equal to part A says find fog. Okay, So here we go. I'll write all my notation so we get used to it. And we remember what it means. Plug in the g, x cubed plus 1, into f. So that's going to go in here. Okay. So that'll be the cube root of x cubed plus 1 minus 3, which is cube root of x cubed minus 2.
And where did you get the -3?
That's part of this f function, right? X minus 3. This x is replaced with the g. So right here, this is what I input. You could put in parentheses so it's more obvious. That's the g. So this is fog. Does that make more sense?
So you're just inserting like the X, basically. That's just.
Yeah. Yeah, don't forget, right? What does this mean, right? This means this is an input into f. So it doesn't matter what the input is, you just follow the rules like we've always done. I'm inputting that input here, even though it looks weird. That's what I'm doing. Any other questions on part A? Okay, let's do Goff. Part B says find Goff, G of f. So that'll be G of cube root which means plug in the cube root and then cube it, right? That becomes x minus 3 plus 1, which is x minus 2. Is part B straightforward? Does it make sense?
Yes.
All right. Oh man, I picked a stupid example. Oh, that's okay. No, actually, there isn't a better one, and it's creative. Okay, so part C. Find the domain of f. I'll go ahead and write the function. Is there anything you can't plug in here? It's an odd root. If you were to graph this, you'll see it. Button is for cube root. Hubert. So we'll use the power notation instead. we agree that 1/3 is the same as cube root, right? So as you can see, all the x values are accounted for. There is no problems. You can plug in any x you want because it is not an even root. Square roots have problems because it's an even. Fourth roots, sixth roots, eighth roots, same problem, right? Cube roots is not a big deal. Okay. As you can see, square root has to keep the inside positive. So it starts here and keeps going, but the red one goes everywhere. Okay. So the domain is all real numbers. A domain of G, that would be x cubed plus 1. Is there any number that you can't cube and then add 1 to it? And if you remember the graph, does it cover all the x values?
No, did it? I think it was 3, right? Except for 3, like 3 and everything else.
This one?
Yeah.
You
I
never-
forgot. I need to see the graph again.
Yeah, let's look at the graph to be sure, right? If you're in doubt, you can always graph it. But the question you should ask yourself is basically, is there a number that I can't cube? I mean, I can cube whatever the hell I want. There's no problem. I can add 1 to anything I want. So yeah, it should be all real numbers. Eventually it keeps going all the way to the left, all the way to the right, forever. Eventually it covers the x values. Okay. Okay, so part E is the hard part. So find the domain of fog. So you need to look at the G function. Did the G have any issues, right? No. All real numbers are fine. When you created fog, did you create a function that had new issues that the G didn't? And we graphed this earlier, right? Something similar. There's no issues here. So if there's no issues in the result, and there's no issues with the G, then the domain of the composite will be everything. Does that make sense? Like how you find it?
And maybe we could do another one.
Yeah, let's do the other direction. G of f. Does the f function have any issues? Did you go to the f? No. Okay, so the one that went inside didn't have any problems. The result that we found, does that have any restrictions?
2, I guess,
What happens if you plug in 2?
and 0.
And 0 is okay, right? Nothing wrong with 0. There's no division by 0. There's no negative even roots. There's no problems. So if there's no problems in the new function that you made, and there's no function in the one that went inside f, then the domain is everything. It all depends on the restrictions of the functions.
So I guess we should just worry if it's like a fraction.
Yeah, like if the result comes out to be like a square root or an even root or a fraction, yeah, 1 over x or something, then yes. Let me see if I can give you a visual here. Let's say we had a g function of a square root of x minus 2. Okay, so we can see that the domain is 2 until infinity, right? I cannot go below 2.
And what about the reflections?
Well, reflection would be a different function. Depends what's happening. You'd find the domain the same way. It'll just be wherever it's facing. Okay, so let's say we composed it. So right here, so let's say you have an f and a g. I want to make a new example that's a little harder, because the ones in the homework are a little too easy. Let's say we wanted to find off, right? That means you plug in the f inside the g. So that would be g of the square root which would be the square root and then you have that. Let's make this a 3. Well, that's fine. So that this is Goff. So the one that went inside was the s function. So the one that went inside had a restriction that it must be right this domain right here. This has a domain of 2 to infinity, right? That's the worst infinity symbol ever. A little better. So that's the domain of f. Obviously, the domain of g is all real numbers, right? The result, does this have new restrictions or does it have the same restrictions as before?
I guess it cannot be negative. Cause it's a, I don't know, cause it's even, it's a 2, I guess so.
Yes, as it's an even root, the inside cannot result in a negative. So the biggest, the smallest number you can choose in here is 2, right? That's why this one right here has a domain of 2 to infinity. So both the result and the original have the same restriction. Do you see that?
So I guess you could say x has to be a greater than or equal to 2. I guess so.
Yeah, for sure the x has to be greater than or equal to 2. So the domain of Goff it happens to be in this case the same as the one that went inside the F. So you look at the any new restrictions that appeared here, and it didn't have any new ones. And you look at the restrictions of the one that went inside the F, and you put that together, and we end up with the same thing. If this would have had a new restriction that wasn't there to begin with, then you'd have to combine that with the restriction of the function that went inside this guy right here. Does that make sense? It's hard to explain that. Is it clear? The homework has easier examples, but I wanted you to see like how you found them if it was more complex. Okay. Okay. Alrighty then, let's see. Let's move on to something else then. Um, Yeah, 2.7. And 2.7 is about inverses. There's a lot of theory behind the requirements for an inverse. The main thing I need you to remember is it needs to be 1-to-1, meaning every x value only goes to a different y value. Okay. Basically look and see if anything repeats. For example, let me give you a function that is not 1-to-1. This is a function because it passes the vertical line test, right? It is not 1-to-1 because it fails the horizontal line test. So these two values, these two x values have two different outputs. So right here, let's look at the easy value. 1 and -1 both go to the 1. and 1. So if you see a y value have two different x's, or you see the y value repeat, then it's not 1 to 1. Okay. There's two things you can look out for. So let's go back to the homework here. So look at these x values. Nothing repeats, right? None of the y's repeat, so we're good. It is 1 to 1. So if it is 1 to 1, then that means you have an inverse. This is 1 to 1, right? All the x's have a different y value, and it passes the horizontal line test. So if you draw horizontal lines, right? It'll only hit the line at one time, but over here it hits twice. So if it hits twice, it is not 1 to 1, which means there is no inverse. It's not going to happen. So you cannot find an inverse of a function if it is not 1 to 1. And 1 to 1 means basically every x has exactly one y for every single x. Okay. Look at this one. You see the problem with this function, why it's not 1 to 1.
I mean, there's two 10s.
Yeah, x, the 2 goes to a 10 and the 6 goes to a 10. These two x's go to the same place, so not 1 to 1, which means no inverse.
What if it was the other way around? So there was a double X, but then only singles on the FX.
Like, would they be
Would that
different?
still be an inverse function? So like, for example, if it was a 2 to 10 and then a 2 to 5.
Oh, you mean like if they were inverted?
Yeah,
Let's see here. That would no longer be a function. That would fail the definition of a function,
okay.
which means we can't talk about 1 to 1.
Mm-hmm.
That's a good question. Does everyone understand what the definition of 1 to 1 is?
Yes.
Could you actually elaborate on it? Like
Yeah.
summarize it, what it means?
Yeah, so basically, here, let me give you the legit definition. Let me pull up the book. It's a nice little visual, actually. One moment. I think this will help right here. I like this picture. All right, so every single x has exactly one unique pair. This is important because if an inverse allows you to go from the output back to the input, so inverse sends me back home. So it needs to be a 1-to-1 correspondence. I can't have these going in the same place because then how do I invert that? That's the idea. Okay, like for example, right here, you have a bunch of x values going to the same place. So if I wanted to undo that, like how do I know which way to go? Do I go to this one or do I go to that one? If I'm going to do an inverse. So an inverse function undoes whatever a function has done. So like if you have a function that squares something, then the inverse would be a square root function, would undo the square. but it
So
needs to
in,
have a specific, yeah, go ahead.
so in that figure B, if the numbers was reversed, like how we said inverted, so it was the double X's, it would just not be a function whatsoever and we couldn't continue from there.
Yeah, it would no longer be a function, so we would not talk about one-to-one.
Okay, so only if it's the other way around with the g of x, if there's a double input for the x, then we can do the one-to-one.
Yeah, so yeah, every x has to have every x in the function has a unique y output. If
Okay,
that
that
happens,
makes, yeah, that's
then
better.
it is one-to-one. And in the notes in the video, it gives you the wordy definition. And it'll give you a notation like this. So this outputs are only equal if the inputs are the same, meaning you're not going to get figure B scenario. But anyway, so that's required in order to talk about inverses. So that's why they're talking about this here. They're wondering, okay, well, is there an inverse? Well, that depends. Is your function one-to-one? So that's what you're looking for. So you can do one horizontal line test. You can look at the inputs, and then of course you can graph it and just see. And there's a theoretical one, which we'll do in 11, how you can verify if something is an inverse or not. Let's do 12. One moment. Okay. Sorry about that. Someone's blowing up my phone. Example 1. All right. Verify that f and g are inverses. So let me give you a note here. F of x and g of x is, or sorry, are inverses of each other if and only if these two things happen. F of g is equal to x and g of f is equal to x. So if you compose them, do the fog and the goff, and you cancel out and give you an x, then they are inverses of each other. So for this example, f is x cubed plus 2. G is cube root x minus 2. Okay. Yep. F of G means F of G, which means F of cube root x minus 2, which would be cube root of x minus 2. Parentheses look stupid. So the cube root cancels with a cube, leaving me with x minus 2. Negative 2 plus 2 cancels, leaving me with an x. So far, this direction, number 1, has been met. So now the C of 2 is also going to work out. So G of F of x means G of F, which means G of x cubed plus 2, which will be G cubed x cubed plus 2 minus 2. So both directions, 1 and 2, give me an x. So we have verified that f and g are inverses of each other. Any questions on this algebra here? Does that make sense?
Can you hear me, sir?
Yes.
Sorry, my mic's been, sometimes it won't turn on.
No worries. Do you have a question?
Oh no, I just want, because I don't know, it's been kind of quiet, so I just wanted to say I understood.
Okay, thanks, appreciate it. Okay, so once you're done on the exam, you'll have something like this where you verify 2 functions, and if you get x on both directions, you're good. If one of them turns out to not be an x, then they are not inverses. You would just say no, because that happened. Yes, because this happened. But it has to be both directions to prove that they are inverses. So that's what they do here. They show the notation. So this is a better problem done on paper. On the computer, it's kind of weird. Maybe even too simple. So they're not really showing what we did. So keep that in mind. So I recommend doing this on paper for 12. Okay. Let's move on to 13. All right, so 13 requires more theory. So I really hope you watch the videos for 2.7. There's a lot of ideas in the background. So in the notes, they said that when you have a function, so let's say you have, it's real quick. And you know what, it'd be better to do it on paper. Well, hold on before the example. If f has domain and range A, comma, B, respectively, and G has domain and range C, comma, D, respectively, you know what? The last part is unnecessary. We don't need this last sentence here. The G part. Okay, so basically what I'm saying, if F has domain range AB, meaning the domain is A, range is B, right? Then F inverse has domain B and range A. They get swapped. So you switch them. So for example, let's say that f of x, let's make up a question right now. Given one, two, three, four, and you get outputs of, I don't know, 2, 4, 6, 8. Let's call this guy f, right? The domain would be 1, 2, 3, 4. The range would be 2, 4, 6, 8 for the f of x function. But for the inverse, it would be the opposite. 2, 4, 6, 8. 1, 2, 3, 4. This would be for f inverse. So the -1 that you see in the notes or in the book means the inverse of f. So remember what we said, right? So this particular function is doubling my numbers, right? It takes the 1, makes it a 2. Takes the 2, makes it a 4. See that? The inverse undoes whatever the function did. That's the purpose. It's a very important idea. So if it's already double, what cuts it in half? 2 goes to 1, 4 goes to 2, 6 goes to 3, etc. So that's a property of functions and their inverses. Does that make sense? Okay. It's going to help in order to do the graphs. So if you have the graph right here, notice by the domain of f, but it would be 0, 1, 2, 3, 4, 5. So I'm going to assume it stops at 5. It goes to 0, goes all the way till, you know what? We'll just write them out. 0, 1, 2, 3, 4, 5. Range. well, 0 goes to 1. 1 goes to 0 goes to 1, 1 goes to 2, it looks like. Right. 2 starts to get kind of weird there. 2 goes to, no, actually 2 is a little bigger than that. 2 point, maybe 5-ish. 3 is about 2.9 maybe. 4 looks like it's at 3. And the exact numbers don't matter. I'm just trying to help you visualize here. 5 is like 3.1. Right. Okay. So knowing that. So I'm going to swap these. So that means that the domain for the inverse, right? For the inverse has to be these. And the y values have to be this. So for F inverse, the range should be 0, 1, 2, right? All the way to 5. So look at these values. This doesn't go to 5, does it? These go to 5. And so do these. But this has a negative value. We didn't have any negatives for our domain and ranges. So even if I switch these two around, right? If I swap these, there's no way I'm going to get negative values. Just not going to happen. So it has to be C. Does that logic make sense?
But what happened if they cross the x-axis?
What do you mean?
What happens if it crosses if it crosses the x-axis and it has negative values?
Oh, it doesn't matter.
Mhm.
Just figure out what is the domain. This didn't have any negatives or domain or range. So it doesn't make sense for the inverse to have negatives. It should not. If the original had negatives, then the inverse should also have negatives. Depending, right? So if this was pointing that way, then we would have negative x values. So the range would be negative. So this is my F. This is the F inverse. Okay. Don't really care about these types of graphs. Oh, oops. For 16, 17, 18, 19, 20, all these right here, all you have to do is graph them and then check, does it pass the horizontal line test? So at the very beginning, we talked about that. So look at 2 over x squared. You see how this does not pass the horizontal line test, right?
Correct, sir.
So you would say no. Does not have an inverse. Graph this guy, and you're going to see that it does pass, so you say yes. But then you have to find it. So let me show you how to find it on 17 and 18. So I'm going to shorten up the question. Find the inverse of f of x equal to, let's do the line first because it's a little easier. And then we'll do a harder one. 3x plus 7. So step 1 to find the inverse is change f of x into y. Step 2, swap x and y. Step 3, solve for y. So subtract the 7, divide by 3. That gives us y equal to x minus 7 over 3. Step 4, change y into f inverse. So the answer would be f inverse of x is equal to x minus 7 over 3. Any questions on how to find an inverse or for this particular example? Okay. Let's do one more, and I think that'll be it for section 2.7. I'll let you go after that. Find the inverse of let's see, is there a hard one? This one looks stupid. 5x plus 3. So step 1, change f of x into y. Step 2, swap the x's and y's. Step 3, solve for y. In this case, I'm going to have to square both sides, right? Okay. Scoring cancels the radical. Solve for y, subtract the 3 over. Divide by 5. So y is equal to this thing here. And once you solve for y, change it to the inverse. This is the inverse. The only thing is, remember that x must be greater than or equal to 0. You have to have a restriction for a square. Because otherwise you'll have both sides and it's gonna fail the horizontal line test. But I think this will be given to you on the homework. Any questions on number 4?
Also, like for the x greater than or equal to 0, so that will cause it to be undefined, or
That would allow this function to be 1-to-1. Because if I don't put the restriction, this is not 1-to-1, which will mean it has no inverse, which is a problem. All right, guys. Let's see, we are on. So next time we'll start 5.1 and 5.2. It's not too bad. We're just going to talk about the theory, or the definition of exponential and logarithms, and talk about the graphs. It won't be too deep as far as problem solving or anything. Next week will be the harder stuff. So I think 2.6 and 2.7 will be the harder sections this week. 5.1 and 5.2 will be kind of chill. And then we'll start 5.3 next week. Okay.
Okay, sounds good.
All right. Well, I just started grading the